Black holes are eating time itself. You've seen the famous black hole image from 2019, but what's happening at their mysterious boundaries where physics breaks down completely? By the end of this documentary, you'll understand how black holes stretch the fabric of space-time, the paradox of information preservation inside them, and what the James Webb Telescope's latest research reveals about these cosmic phenomena. Whether you're a physics enthusiast or simply curious about the universe's greatest mysteries, you're about to discover how black holes fundamentally challenge our understanding of reality, transforming not just what we know about space, but about the very nature of time and existence itself. Einstein's revolutionary prediction. In 1915, a humble patent clerk turned physicist accomplished what many before him couldn't. He completely reimagined gravity. Albert Einstein's general theory of relativity represented a fundamental shift in how we understand the universe. While Newton saw gravity as a force acting across space, Einstein revealed it was a curvature in the fabric of space-time itself. The implications were profound. Massive objects like stars warp the space-time around them. Visualize space-time as a stretched rubber sheet with a grid pattern. Place a heavy ball in the center, and it creates a depression, bending the grid lines. Smaller objects naturally roll toward the larger mass, not because of some mysterious attractive force, but because they're following these curved paths in space-time, like marbles rolling along the depressions in the sheet. Einstein's equations contained something even he didn't anticipate. When mathematicians explored solutions to his field equations, they discovered that if mass became concentrated enough, space-time could curve so severely that nothing, not even light, could escape its gravitational influence. The mathematics pointed to the existence of what we now call black holes, though that term wouldn't appear for decades. Einstein himself rejected this implication. In a 1939 paper in the Annals of Mathematics, he attempted to prove that these Schwarzschild singularities were merely mathematical artifacts. He wrote that the essential result of this investigation is a clear understanding as to why the Schwarzschild singularities do not exist in physical reality. Einstein believed the laws of physics would prevent matter from reaching such extreme concentrations. While Einstein grappled with his own theory's implications, Carl Schwarzschild made critical advances under extraordinary circumstances. Serving on the Russian front during World War I, Schwarzschild solved Einstein's complex field equations in late 1915 while suffering from a rare autoimmune disease. He sent his solutions to Einstein from the battlefield, and Einstein presented them to the Prussian Academy. Tragically, Schwarzschild died in May 1916, never witnessing how his work would transform our understanding of the cosmos. Schwarzschild's solution identified a critical mathematical boundary, now known as the Schwarzschild radius. For any given mass, this radius marks where escape velocity equals the speed of light. Within this boundary, space-time curves so severely that all paths lead inward. Even light becomes trapped in this gravitational well. The boundary itself became known as the event horizon, the point of no return. The Schwarzschild radius follows a simple formula. Rs equals 2gm/c superscript 2. For an object with our sun's mass, this radius would be just about 3 kilometers. Earth would need to be compressed to the size of a pea. Creating a black hole required extraordinarily dense conditions that seemed implausible to early 20th century scientists. For decades, these mathematical curiosities remained theoretical possibilities that most physicists dismissed. Throughout the 1920s and 1930s, only a handful of scientists continued exploring these exotic solutions. Among them was Subrahmanyan Chandrasekhar, who calculated in 1931 that stars with masses greater than 1.4 times our sun couldn't support themselves against gravitational collapse after exhausting their nuclear fuel. Chandrasekhar faced fierce resistance from prominent astronomers like Arthur Eddington, who declared that there should be a law of nature to prevent a star from behaving in this absurd way. The scientific community rejected the possibility of stars collapsing to infinite density. The mathematics pointed that direction, but many believed nature must have other mechanisms at work. Despite this resistance, theoretical exploration continued. In 1939, Robert Oppenheimer and Hartland Snyder published calculations showing that massive stars could indeed collapse under their own gravity, forming what we now recognize as black holes. Their paper described how the collapse would appear different to observers at different locations, pioneering concepts like gravitational time dilation that are fundamental to our modern understanding. This theoretical work occurred without observational evidence. No telescope had captured these extreme objects. For decades, black holes remained mathematical ghosts, solutions on paper that might or might not correspond to physical reality. This disconnect between theory and observation fueled ongoing skepticism. The gap between prediction and confirmation highlights how science sometimes progresses. Mathematics often points toward realities that technology can't yet detect. Einstein's equations predicted gravitational waves in 1916, but direct detection didn't occur until 2015, nearly a century later. Similarly, his theory contained the seeds of black hole physics decades before astronomers could provide observational evidence. The black hole story illustrates scientific theory evolution perfectly. The same equations Einstein developed to explain Mercury's orbit and starlight bending contained objects so extreme they seemed to defy common sense. Yet the mathematics was unambiguous. If general relativity correctly described gravity, and all evidence suggested it did, then these strange objects weren't just possible but inevitable under certain conditions. This mathematical prediction laid the groundwork for understanding how these objects distort spacetime. Near a black hole, time slows down. Space stretches and warps. Imagine light rays as straight lines on our grid. Approaching a black hole, these lines bend increasingly until they spiral inward, unable to escape. The familiar rules governing everyday experience break down completely. All these bizarre effects flow directly from Einstein's 1915 theory, despite his resistance to some implications. The vindication of these early mathematical predictions would take decades. Not until the 1960s and 1970s would astronomers begin finding observational evidence suggesting these objects might actually exist. But the theoretical foundation was already established, awaiting observational techniques to catch up. From mathematical curiosity to physical reality. In 1916, the mathematics pointed clearly to a startling possibility, but the physics community remained unconvinced. Even with Schwarzschild's solution establishing the theoretical framework, physicists across the globe regarded these dense gravitational objects as mathematical curiosities, elegant solutions on paper that couldn't possibly exist in the actual universe. The concept simply seemed too extreme, too perfect in its mathematical symmetry to manifest in the messy reality of space. Scientific skepticism toward gravitational collapse persisted for decades. Through the mid-20th century, the prevailing belief held that some fundamental physical principle would prevent stars from collapsing to such extreme densities. The quantum mechanical effects creating outward pressure seemed sufficient protection against such catastrophic endings for stars. The hunt for actual evidence began with an unexpected discovery in the early 1960s. Objects later named quasars. The first, designated 3C273, appeared star-like through optical telescopes, but emitted radio waves of unprecedented intensity. Spectral analysis revealed something remarkable. These tiny points of light were billions of light years distant, yet shining with the brightness of 1 trillion stars. Their energy output was concentrated in regions smaller than our solar system. This discovery coincided with growing interest in Cygnus X, 1, a powerful X-ray source identified in 1964. Observations revealed a binary system where a blue supergiant star orbited an invisible companion. Calculations indicated this unseen object exceeded 9 solar masses, far too heavy for a neutron star. The X-rays originated from superheated gas spiraling toward this invisible object, creating a signature consistent with what theorists predicted from matter falling into a black hole. While astronomers gathered this observational data, the scientific community proposed numerous alternative explanations for quasars' extraordinary energy output. Some suggested unusual types of stars with exotic properties, while others proposed entire galaxies experiencing enormous bursts of star formation. A few theorists even speculated about tears in spacetime itself. However, each alternative theory failed to account for both the extreme luminosity and compact size consistently confirmed by observations. The theoretical pieces began aligning with observational reality. A growing group of physicists considered that perhaps quasars were powered by gravity itself, specifically by matter falling into extraordinarily dense objects at galactic centers. The gravitational energy released from this infalling material could theoretically generate the observed luminosities, but accepting this explanation meant acknowledging the existence of objects that had thus far been mathematical abstractions. The concept received its memorable name in 1967 when physicist John Wheeler coined the term black hole during a conference. Presentation. This evocative phrase captured the essence of these gravity wells from which not even light could escape. Wheeler's terminology provided more than nomenclature. It helped transform abstract mathematical entities into subjects of serious astrophysical investigation. The debate about Cygnus X, one's nature, became emblematic of the shifting scientific consensus. Stephen Hawking and Kip Thorne famously wagered on its nature in 1974, with Hawking betting against it being a black hole. By 1990, as evidence accumulated, Hawking conceded the bet, acknowledging that Cygnus X, one almost certainly contained a black hole. This scientific wager symbolized the broader transformation occurring throughout astronomy. Observational techniques advanced considerably through the 1980s and 1990s. Radio telescopes using very long baseline interferometry allowed astronomers to study galactic centers with unprecedented detail. These observations repeatedly revealed compact radio sources consistent with supermassive black holes, objects millions or billions of times more massive than our Sun, confined to incredibly small regions. Perhaps most convincingly, astronomers tracked star orbits at our own Milky Way's center. These stars circled an invisible object called Sagittarius A*, with velocities indicating approximately 4 million solar masses concentrated in an extraordinarily small volume. No known astrophysical object except a black hole could account for this mass concentration in such limited space. The scientific paradigm shifted dramatically by the late 1990s. What began as a controversial mathematical solution became recognized as fundamental to cosmic architecture. Astronomers accepted that most large galaxies harbor supermassive black holes at their centers, with these objects playing crucial roles in galactic evolution. Smaller stellar mass black holes, scattered throughout galaxies, were acknowledged as inevitable endpoints of massive star evolution. This transformation from theoretical possibility to accepted astrophysical reality spanned more than 5 decades. The journey required advances in observational technology alongside a fundamental shift in scientific thinking, a willingness to accept that the universe could manifest phenomena that initially seemed too extreme to be plausible. The story of black holes reveals something profound about scientific progress. Initial skepticism toward mathematical predictions gradually yields to observational evidence, even when that evidence points toward realities that challenge conventional understanding. The mathematics of 1916 had indeed revealed a cosmic truth, though it would take generations of scientists and technological advancements to fully recognize it. These gravitational behemoths, once dismissed as impossibilities, now stand as cornerstones of our understanding of the cosmos. Objects where matter, energy, space, and time reach their most extreme manifestations. The warping of time. While scientists eventually accepted black holes as physical entities, there's something even more unsettling about them than their gravitational pull. What happens to time itself near these cosmic monsters challenges our fundamental understanding of reality. As strange as it sounds, time doesn't flow at the same rate everywhere in the universe. And nowhere is this more dramatic than in the vicinity of a black hole. Einstein's theory of general relativity revealed that gravity warps the fabric of space-time itself. This warping affects both the path objects take through space and literally changes how time flows. Near massive objects, time slows down relative to regions with weaker gravity. This is a measurable fact of our universe called gravitational time dilation. The mathematics behind this phenomenon is described by the Schwarzschild metric, a solution to Einstein's field equations that describe space-time around a spherically symmetric object like a black hole. As you get closer to a massive object, the time basis vector contracts. Think of it like watching a video in slow motion. The closer to the black hole, the slower the playback speed becomes from an outside perspective. To quantify this effect, the GDT component of the Schwarzschild metric is defined as GDT equals dash 1 rs/r. Here, rs represents the Schwarzschild radius, the boundary of the black hole's event horizon, and r is your distance from the center. As r decreases, time dilation becomes increasingly pronounced. The practical implications are mind-bending. At a distance of just 1.5 times the Schwarzschild radius, time passes so differently that for every 24 hours experienced near the black hole, about 41.6 hours would elapse back on Earth. Move even closer to just 1.00005 times the Schwarzschild radius, and the difference becomes extreme. For every single year you experience near the black hole, 141 years would pass on Earth. Similar principles affect technology we use every day. GPS satellites must account for time, dilation effects to function properly, without correction for the fact that time flows slightly faster in orbit than on Earth's surface due to weaker gravity at higher altitudes. GPS positioning would drift by about 10 kilometers per day. The famous twin paradox illustrates this dramatically near black holes. Imagine an astronaut orbiting just above a black hole's event horizon while their twin remains on Earth. When a spacefaring twin returns home, they would find their Earthbound sibling had aged decades or even centuries more. This is like two people starting the same movie simultaneously. The person near the black hole sees only the opening scenes while the Earthbound person has watched the entire film, its sequels, and perhaps the entire franchise. Perhaps the most bewildering aspect appears when we consider what happens to someone falling into a black hole, as seen by a distant observer. From the perspective of someone watching safely, the falling person would appear to move increasingly slowly as they approach the event horizon. Their image gradually redshifts, light waves stretching to longer wavelengths due to the extreme gravitational field, making them appear redder, dimmer, and moving more sluggishly. As they reach the event horizon itself, they would appear to freeze completely. Their image becomes increasingly redshifted until it fades from visibility, but mathematically, they never quite cross the horizon in our reference frame. From an external vantage point, time essentially stops at the boundary of a black hole. At exactly the event horizon, the time component of the metric shrinks to zero, indicating infinite time dilation. This represents a fundamental property of space-time in extreme gravitational fields. What makes this particularly fascinating is the difference between perspectives. From a falling person's own viewpoint, nothing special happens at the event horizon. They continue falling inward, experiencing time normally in their reference frame. This disconnect highlights how profoundly gravity distorts our assumptions about reality. Black holes don't suck time. They warp space-time's geometry. If you could somehow hover near a black hole, requiring enormous energy to counteract gravity, you would experience time passing normally from your perspective. Your watch would tick at its usual rate, and your heart would beat as always. But looking back at Earth through a telescope, you would see everything happening in fast forward. People moving incredibly quickly, seasons changing rapidly, civilizations rising and falling in what seems like moments to you. This relativistic effect is crucial when considering how information behaves near black holes. Any signal sent from near the event horizon would be extremely redshifted, like stretching a single spoken word across years. This creates an effective communication barrier between regions of extreme space-time curvature and the rest of the universe. Regions very close to black holes become increasingly isolated from the cosmic conversation. Their signals stretched over longer periods in the outside universe's reference frame. A 1-second message sent from near the event horizon might take years or centuries to complete from an Earth observer's perspective. The most extreme manifestation occurs precisely at the event horizon, where space-time curvature becomes so severe that light itself can no longer escape. The time component of the Schwarzschild metric goes to 0, indicating that time, from an outside perspective, effectively stops, creating the appearance of a frozen surface where infalling matter appears to collect but never quite cross over. The ultimate cosmic stretcher. This apparent freezing at the event horizon masks an even more terrifying reality for anyone unfortunate enough to fall toward a black hole. At a precisely calculable distance from the black hole's center, which varies depending on the black hole's mass, the difference in gravitational pull between your head and feet becomes strong enough to overcome the electromagnetic forces holding your body together. Physicists call this phenomenon spaghettification, a surprisingly straightforward term for one of the most violent processes in the universe. Spaghettification results from tidal forces, a physical reality caused by gravity's weakening with distance according to the inverse square law. When you stand on Earth, the gravitational pull on your feet is very slightly stronger than on your head, but the difference is imperceptible. Near a black hole, this gradient becomes extreme, creating forces that transform a three-dimensional person into what resembles a one-dimensional stream of particles, like cosmic taffy stretched beyond recognition. Approaching a stellar mass black hole feet first, the gravitational force on your feet might be millions of times stronger than on your head. Simultaneously, the black hole's gravity compresses you horizontally, squeezing your body. From the sides, while stretching it vertically, your body would elongate dramatically, thinning like spaghetti being pulled from both ends while compressed from the sides. The mass of a black hole determines where this spaghettification process begins. For a typical stellar mass black hole, one with about 10 times the mass of our Sun, you would experience noticeable stretching forces well before reaching the event horizon. The tidal forces grow so rapidly that your body would be completely torn apart while still hundreds of kilometers away from the point of no return. Supermassive black holes, counterintuitively, offer a less immediately deadly experience. With masses millions or billions of times that of our Sun, these cosmic giants have much larger event horizons and more gradual gravitational gradients. For Sagittarius A*, the supermassive black hole at the center of our galaxy, you could theoretically cross the event horizon without feeling extreme tidal forces. The differential gravity would still be present, but not yet strong enough to overcome the electromagnetic bonds holding your atoms together. This temporary reprieve is fleeting. Once inside the event horizon of any black hole, spaghettification becomes inevitable as you approach the central singularity. The structural breakdown follows a predictable sequence. First, your body's cohesion fails as tidal forces exceed the strength of your connective tissues. This happens when the differential gravitational pull between extremities surpasses about 1,000 newtons, far less than needed to tear apart steel, but sufficient to overcome human tissue. Your limbs would separate, joints would dislocate, and tissues would stretch like warm caramel pulled apart. As tidal forces intensify, molecular bonds begin to break. The chemical bonds maintaining complex organic molecules, including proteins, DNA, and cell membranes, require specific geometries to remain stable. The extreme stretching distorts these configurations beyond sustainable limits, causing molecular disintegration. Your cellular structure would collapse as the molecules comprising your cells are pulled into increasingly linear arrangements. In the final phase, atomic structures themselves fail. The electromagnetic forces holding electrons in orbit around atomic nuclei become overwhelmed by the gravitational gradient. Atoms stretch and distort until they lose their integrity, resulting in complete atomic disintegration. What was once a person becomes an elongated stream of subatomic particles. What makes this process particularly fascinating is the contrast between the experience of the falling observer and distant witnesses. From your perspective, as the unfortunate traveler, time would continue flowing normally. You would experience the full horror of spaghettification in real time, feeling your body being stretched and compressed until consciousness ceases. Yet for someone watching from safe distance, your descent would appear dramatically different. As you approach the event horizon, severe time dilation would make your fall appear to slow to a crawl. The observer would see you stretching out more and more gradually, with the process appearing to freeze completely at the event horizon itself. Your image would remain there, stretched and distorted, but seemingly permanent. A macabre monument to the black hole's gravitational power. This visual freezing creates another strange effect. From a distant perspective, black holes never actually appear to consume anything. Matter falling into them seems to pile up at the event horizon in an increasingly redshifted, time-dilated state. The black hole appears to develop a thin atmosphere of stretched, frozen material. For stellar mass black holes, we can calculate the exact distance at which spaghettification begins. For a person approximately 2 meters tall approaching a 10 solar mass black hole, noticeable stretching would begin at around 1,000 kilometers from the center, well outside the event horizon, which would be just 30 kilometers in radius. Remarkably, we can observe this process on an astronomical scale. When stars are torn apart by supermassive black holes, called tidal disruption events, they produce distinctive radiation signatures detectable across billions of light years. Astronomers have documented numerous such events, providing real observational evidence of spaghettification. As the star approaches, it stretches and compresses just like a human body would, but on a vastly larger scale. The star's material heats up during this violent process, emitting bright flares of radiation across multiple wavelengths before the stellar remnants vanish beyond the event horizon. Spaghettification demonstrates how gravity, when concentrated sufficiently, overcomes the electromagnetic force governing our everyday experience of solid matter. This breakdown of fundamental forces reveals the true nature of the information paradox. Beyond the physical destruction lies a problem so profound it has split the physics community for nearly half a century. Imagine tossing an encyclopedia into a black hole and waiting billions of years for it to evaporate. What becomes of the information printed on its pages? According to quantum mechanics, that information can never be truly destroyed, yet black holes seem to do exactly that. At the heart of modern physics sits a principle that sounds almost philosophical. Information cannot be destroyed. This isn't about books or data files, but about the fundamental state of every particle in the universe, its position, momentum, spin, and other quantum properties. According to quantum theory, if you knew the exact state of every particle in the universe at any moment, you could theoretically calculate both the past and future states of the entire cosmos. The equations of quantum mechanics are reversible, meaning they work equally well going forward or backward in time. This conservation of information stands as a cornerstone of physics, supported by decades of experimental evidence. Yet black holes present a glaring contradiction. When matter falls into a black hole, all of its distinctive properties, the quantum information that makes it unique, seem to vanish behind the event horizon. The black hole grows slightly in mass, but otherwise retains no trace of what fell in. It's like watching history itself being erased from the universe's perfect ledger, leaving blank pages where detailed records once existed. The situation became even more puzzling in 1974 when Stephen Hawking made his groundbreaking discovery about black holes. Through complex calculations combining quantum field theory with general relativity, Hawking demonstrated that black holes emit a faint radiation, now called Hawking radiation, caused by quantum effects near the event horizon. This radiation has a peculiar property. It appears completely random and thermal, carrying no information about what's inside the black hole. The radiation causes black holes to lose mass over time, eventually evaporating completely. A stellar mass black hole would take approximately 10 to the power of 67 years to evaporate, far longer than the current age of the universe. But the theoretical endpoint is clear. The black hole eventually disappears. Herein lies the paradox. If a black hole eventually evaporates away completely, what happens to all the information it ever absorbed? If the information truly vanishes, then quantum mechanics is wrong at a fundamental level. If the information somehow escapes, how does it do so when Hawking radiation appears completely random? This question has generated three main theoretical responses. Option 1. Information is genuinely destroyed in black holes. This radical position would require a profound revision of quantum theory, undermining the principle of information conservation that has guided physics for a century. Few physicists embrace this option, given the extraordinary success of quantum mechanics in every other domain. Option 2. Information is preserved in subtle correlations within the Hawking radiation. Under this view, the radiation only appears random to our limited measurements, but actually contains encrypted information about everything that fell into the black hole. Hawking himself eventually supported this position after initially arguing for information loss. Physicist Leonard Susskind proposed the black hole complementarity principle, suggesting that information can simultaneously be inside the black hole for a falling observer and encoded in the radiation for an outside observer. Option 3. Information is stored through more exotic mechanisms. Perhaps it remains in a small remnant after evaporation, or transfers to a parallel universe through microscopic wormholes, or records itself on the interior surface of the event horizon. This last possibility connects to the holographic principle, first proposed by Gerard T. Hooft and refined by Leonard Susskind. This revolutionary idea suggests that all information contained in a volume of space can be represented by information on the boundary of that region. Applied to black holes, this means all information about objects that fell might be encoded on the event horizon itself. The holographic principle found its most precise expression in the ADS/CFT correspondence, developed by Juan Meldacena in 1997. This correspondence establishes a mathematical equivalence between a quantum theory of gravity in a space with negative curvature and a quantum field theory without gravity that lives on the boundary of that space. While our universe doesn't have negative curvature, this relationship offers powerful tools for tackling the information paradox. String theory provides another framework for addressing the paradox by modeling black holes as dense collections of strings and higher dimensional membranes. The microscopic states of these string configurations account for the black hole's entropy, suggesting the information remains encoded at the quantum level. The stakes of resolving this paradox are extraordinary. As physicist John Preskill noted, we're talking about whether quantum mechanics is correct as a description of nature. This isn't merely an abstract puzzle. It's a window into the most fundamental aspects of reality. Recent developments have added fascinating dimensions to the debate. In 2019, physicists proposed the firewall paradox, demonstrating that the requirements of information preservation, locality, and quantum field theory near the horizon are mutually contradictory. This paradox forces physicists to reconsider which fundamental principles might need modification. Some theorists, including Hawking in his later years, have proposed that black holes might have apparent horizons rather than well-defined event horizons, allowing information to escape. Others suggest quantum entanglement between particles inside and outside the black hole might preserve information through non-local effects. The information paradox illustrates how scientific progress sometimes comes not from solving problems, but from formulating them precisely enough to reveal deeper contradictions in our understanding. As Niels Bohr once remarked about quantum mechanics, if you're not confused by it, you haven't understood it. Capturing the invisible. While theoretical debates about information paradoxes continued in conference rooms, in 2019 scientists achieved something far more tangible. They captured what no human I had ever seen before. The Event Horizon Telescope collaboration unveiled the first ever image of a black hole, transforming these enigmatic objects from mathematical abstractions into observable reality. This represented visual confirmation of predictions made a century earlier. How do you photograph something that, by definition, swallows all light that touches it? The challenge seemed insurmountable. Black holes don't emit light, nor do they reflect it. Their defining characteristic is that nothing, including electromagnetic radiation, escapes their gravitational pull. Yet scientists found an ingenious workaround. They couldn't see the black hole itself, but they could capture the shadow it casts against the hot gas swirling around it. This achievement required rethinking our very concept of what a telescope could be. Traditional telescopes, even our most powerful space observatories, lack the resolution needed to image a black hole. The angular size of a black hole as seen from Earth is extraordinarily small, comparable to trying to spot an orange on the moon's surface from your backyard. The solution was elegant and ambitious. Instead of building an impossibly large single telescope, scientists created a virtual one by linking radio observatories across the entire planet. The Event Horizon Telescope functions as a synchronized network that effectively turns Earth itself into one massive detection dish. Radio telescopes in locations spanning Hawaii, Arizona, Chile, Mexico, Spain, and the South Pole collected data simultaneously, creating a telescope with an effective diameter equal to our planet's width. Synchronizing these observatories required exceptional technological precision. Each facility used atomic clocks accurate to within a fraction of a trillionth of a second. The collected data was enormous, several petabytes, so massive it couldn't be transmitted over the internet. Hard drives filled with information had to be physically transported from remote observatories to central processing facilities. They selected the supermassive black hole at the center of galaxy M87 as their target. This cosmic monster contains approximately 6.5 billion times the mass of our sun. Despite being 55 million light-years distant, its enormous size made it an ideal subject. Life from this object began its journey toward Earth when dinosaurs still roamed our planet. The imaging technique captured radio waves rather than visible light. The superheated gas spiraling into the black hole emits radiation across the electromagnetic spectrum. The EHD detected this radiation at a wavelength of 1.3 millimeters, which can penetrate the dust and gas surrounding the black hole. The polarization of this light revealed crucial information about the magnetic field structure around the black hole, helping scientists understand how these objects generate powerful jets of particles. When the image was finally assembled after years of data collection and processing, the moment was electric. Scientists gathered around screens, holding their breath as the processing completed. What emerged was both simple and profound. A bright, asymmetrical ring surrounding a dark central shadow. This shadow represented direct visual evidence of the black hole's event horizon, the point of no return beyond which nothing escapes. The bright ring showed superheated gas accelerating to near light speed as it circles before disappearing forever. The asymmetry in the ring provided valuable scientific data. It revealed that material orbiting the black hole isn't uniformly distributed and indicated the direction of the black hole's rotation. The brighter portion corresponds to gas moving toward us, while the dimmer section represents gas moving away, an effect enhanced by relativistic beaming. What makes this image historically significant is its precise match with theoretical predictions. The shape and size of a shadow aligned almost perfectly with Einstein's equations. For a century, physicists had worked with these equations on paper and in simulations. Now, they could compare those predictions with direct observation. The measured diameter of the shadow differed from predictions by less than 10%. Computer simulations had generated visualizations of black holes for decades based on mathematical models. When compared with the actual image, the similarity was striking. The observed image showed the characteristic photon ring, light being bent around the black hole multiple times before reaching us. This image confirmed that supermassive black holes power the enormous energy output of active galactic nuclei. M87 is known for its powerful relativistic jet, a stream of particles ejected from near the black hole at nearly light speed, extending over 5,000 light-years. The HD image connected this jet to processes occurring at the very edge of the event horizon. The resolution required to capture this image equals being able to read a newspaper in New York from a sidewalk cafe in Paris. It represents a triumph of international scientific collaboration, with over 200 researchers from 60 institutions across 20 countries working together. For Katie Bauman, then a 29-year-old computer scientist, the project held special significance. She led development of a key algorithm used to convert the massive data into an actual image. The photograph of her reaction when first seeing the assembled image became almost as iconic as the black hole image itself, capturing the human emotion behind this breakthrough. What we're seeing isn't instantaneous. The enormous distance means we're observing M87's black hole as it appeared 55 million years ago. The light in that historic image began its journey during the Eocene epoch, when early primates were just beginning to appear on our planet. The EHD collaboration continues analyzing data, including observations of Sagittarius A*, the supermassive black hole at our Milky Way center. Though closer to Earth, our galaxy's black hole is much smaller than M87's, making it a more challenging imaging target despite its proximity. James Webb's New Frontier. 1 million miles from Earth, the James Webb Space Telescope has been peering deeper into cosmic history than ever before, uncovering phenomena that challenge our fundamental understanding of the universe's evolution. Unlike its predecessors, Webb's advanced infrared capabilities allow it to detect light that has been traveling for over 13 billion years. Light from the universe's earliest epochs that has been stretched by cosmic expansion into the infrared spectrum. This technological marvel is rewriting our cosmic timeline, particularly regarding black holes. Astronomers expected to find small, nascent black holes in the early universe, but Webb has revealed fully formed cosmic monsters that, according to conventional theories, shouldn't exist yet. The telescope has detected supermassive black holes lurking in galaxies that existed less than 500 million years after the Big Bang. This discovery has sent shockwaves through the astrophysics community because these objects contain billions of solar masses, a scale that should require billions of years to accumulate according to standard formation models. Imagine expecting to find toddlers, but discovering fully grown adults instead. The universe was still in its cosmic infancy, yet these black holes had already achieved masses comparable to those in mature galaxies today. This creates a profound timeline problem. How did these cosmic behemoths grow so massive so quickly? The conventional understanding of black hole formation begins with the death of massive stars, which collapse under their own gravity to form stellar mass black holes. These objects then grow by consuming nearby gas and merging with other black holes, a process that should unfold over billions of years. Webb's observations suggest this gradual growth scenario fails for the earliest supermassive black holes. Webb's infrared instruments act like a cosmic decoder, revealing little red dots, or LRDs, small, extremely red objects in the distant, young universe that were previously invisible to us. Similar to how infrared goggles can see through smoke, Webb can peer through cosmic dust to see heat signatures from the early universe. Follow-up analysis revealed something remarkable, approximately. 70% of these LRDs show evidence of gas rapidly orbiting around supermassive black holes, indicating they are active galactic nuclei. This statistic fundamentally shifts our understanding, suggesting that obscured black hole growth dominated the early universe landscape, rather than being a rare occurrence. The intense radiation and particles ejected by these growing black holes heated surrounding dust, causing it to glow brightly in infrared wavelengths that Webb detects with unprecedented sensitivity. To explain these premature cosmic giants, scientists are developing alternative theories for their rapid formation. One leading hypothesis suggests they form through direct collapse of massive gas clouds in the early universe. Rather than following the usual star formation and eventual collapse process, these primordial gas clouds might have bypassed the stellar stage entirely, collapsing directly into black holes with masses thousands of times greater than our Sun. Another possibility involves rapid mergers of smaller black holes during the universe's first few 100 million years. Perhaps conditions in the early universe, denser gas clouds, closer proximity of proto-galaxies, and different physical properties created an environment where black hole mergers happened far more frequently than today. Some researchers have proposed more exotic explanations involving early universe physics. Perhaps different physical constants or additional dimensions influenced gravitational interactions during the universe's first billion years, allowing black holes to form and grow in ways not possible under current cosmic conditions. Webb's observations provide crucial data to determine which theory is most accurate. By studying light from quasars powered by these ancient black holes, astronomers can analyze their properties in unprecedented detail, determining masses, spin rates, and the composition of their surrounding environments. The telescope has also revealed surprising insights about the relationship between early black holes and their host galaxies. Research teams found that the mass distribution of early universe black holes remains consistent with that observed in the local universe. This consistency across cosmic time suggests that whatever mechanism produces these black holes operates according to similar principles throughout cosmic history. Furthermore, Webb's data indicates that much of the light from these distant objects originates from actively growing black holes rather than stars. This distinction is crucial, as it indicates these early galaxies might contain fewer stars than previously thought, making them smaller galaxies that existing formation theories can more easily accommodate. These observations force astronomers to reconsider the timeline of cosmic structure formation. The standard cosmological model must now account for black hole formation occurring much earlier and more rapidly than previously believed. Webb's unprecedented resolution has also allowed astronomers to study jets emanating from these early black holes. Powerful streams of particles traveling at nearly light speed that extend for thousands of light years. These jets interact with surrounding gas, either triggering star formation by compressing gas clouds or preventing it by heating gas and driving it from a galaxy. By observing these jets and their effects, Webb helps scientists understand how black holes influence the evolution of the earliest galaxies. This relationship between black hole activity and galaxy formation appears established very early in cosmic history, suggesting it's a fundamental aspect of galactic development. As Webb continues its mission, astronomers expect to discover even more distant black holes, possibly pushing the timeline of black hole formation back further. Each new discovery will provide additional constraints on formation theories, gradually revealing how these cosmic monsters came to exist so early in universal history. Galactic architects, from distant cosmic giants to the one in our cosmic backyard. Sagittarius, A*, might be smaller than those ancient behemoths Webb has discovered, but it wields extraordinary influence over our galaxy's fate. Scientists tracking stars orbiting this 4-million solar mass monster have uncovered something surprising. Black holes don't just consume, they create. When astronomers point their instruments toward our galactic center, they witness stars racing in elliptical orbits around an invisible point of tremendous gravitational influence. These stellar movements have provided the most compelling evidence for Sagittarius A*'s existence. Recent observations using the James Webb Space Telescope have revealed dynamic flares of light emanating from our central black hole. These flares, including brief flashes lasting mere seconds and longer, brighter eruptions occurring daily, offer unprecedented insight into how black holes interact with their surroundings. They represent our clearest view yet of black hole activity in our own cosmic neighborhood. Modern research has dismantled the traditional view of black holes as passive cosmic vacuum cleaners. Sagittarius A** functions as a cosmic conductor, orchestrating the symphony of stellar birth and death throughout the Milky Way. It actively shapes galactic evolution through complex feedback mechanisms, creating a delicate dance between the central black hole and the surrounding galaxy. Sagittarius A** regulates star formation through a sophisticated balance of forces. The radiation and energetic jets expelled from its vicinity compress gas clouds in some regions, triggering the collapse necessary for new stars to form. In other areas, this same energy prevents gas from cooling and condensing, effectively suppressing star birth. This regulatory role extends thousands of light years beyond the black hole itself, as jets from active galactic nuclei inject tremendous energy into the galactic environment. Astronomers have discovered a remarkable correlation between the mass of a galaxy's central black hole and the properties of the galaxy itself, a relationship known as the M-sigma relation. This statistical connection suggests that black holes and their host galaxies evolve together. The mass of the central black hole correlates strongly with the velocity dispersion of stars in the galaxy's bulge, implying a coordinated evolutionary history. The synchronization between black hole and galaxy occurs through powerful feedback mechanisms. Matter falling toward a black hole forms an accretion disk that heats to extreme temperatures, converting gravitational potential energy into radiation with extraordinary efficiency, up to 40 times more efficient than nuclear fusion. This energy output regulates the very processes that feed the black hole, creating a self-limiting system. The Blandford's-Najek process explains how rotating black holes extract energy through magnetic fields, powering enormous relativistic jets. These jets, composed of high-energy particles accelerated to near light speed, transform the black hole's rotational energy into kinetic energy that shapes the surrounding galactic environment. Galaxies with active central black holes display powerful jets and high levels of radiation across the electromagnetic spectrum. The intensity of this activity correlates directly with the amount of material falling into the black hole, creating variable influence on galactic evolution depending on the black hole's consumption rate. Evidence suggests that Sagittarius A** was significantly more active in the past. This historical hyperactivity played a crucial role in sculpting the Milky Way's current structure. Today's decreased activity represents just one phase in the long-term relationship between our galaxy and its central engine, a relationship continuing to evolve over cosmic time. Hypervelocity stars provide compelling evidence for Sagittarius A**'s past activity. These stars travel at exceptional speeds that normal stellar dynamics cannot explain. Some researchers propose that an intermediate mass black hole, which may have merged with Sagittarius A** billions of years ago, acted as a gravitational goalkeeper, preventing binary star systems from being disrupted close to the central black hole and influencing the distribution of these high-speed stellar wanderers. The dynamic flares recently observed from Sagittarius A** demonstrate its continuing influence. These eruptions, though less powerful than those in the galaxy's distant past, show that our central black hole remains an active participant in galactic processes. Each flare represents a surge of energy and matter impacting the surrounding interstellar environment. Through these various mechanisms, Sagittarius A** fundamentally alters our galaxy's evolution. By regulating star formation rates, ejecting material through powerful jets, and establishing gravitational domains that dictate orbital dynamics, this cosmic architect has shaped galactic structure over billions of years. This understanding reverses earlier models that viewed black holes as passive objects. We now recognize them as dynamic systems actively shaping cosmic evolution through gravitational influence, energy output, and matter distribution. The relationship between black holes and galaxies is truly symbiotic. Each influences the development of the other in a cosmic feedback loop operating across billions of years. When we observe the Milky Way today, we're seeing the cumulative results of Sagittarius A**''s influence over cosmic time. The distribution of stars, spiral arm structure, and chemical composition of different regions all bear the signatures of our central black hole's past activity. Our galaxy is, in many ways, a product of its relationship with Sagittarius A*. As observational capabilities improve, we're detecting subtler aspects of this relationship. The James Webb Space Telescope's ability to peer through dust clouds with unprecedented clarity reveals details about our galaxy's central regions previously hidden from view. These observations continue to refine our understanding of how Sagittarius bridges through space-time, beyond their role as cosmic architects. Black holes might harbor an even more profound secret. Einstein's field equations contain a solution so bizarre that most physicists dismissed it for decades. The possibility that the darkness inside a black hole could connect to entirely different regions of space-time. In 1935, Einstein himself, working with physicist Nathan Rosen, discovered something remarkable within the mathematics of general relativity. While exploring the Schwarzschild solution that describes space-time around a black hole, they uncovered a theoretical bridge, a connection between two separate regions of space-time. This mathematical curiosity became known as the Einstein-Rosen bridge, the first formal description of what we now call a wormhole. The concept is captivating in its elegance. Instead of ending at a singularity, the extreme warping of space-time inside a black hole might create a tunnel leading somewhere else entirely. This somewhere else could be another location in our own universe, or perhaps even another universe altogether. The mathematical solution suggests that a black hole might be connected to a white hole, a theoretical object that, unlike a black hole, allows matter and energy to exit but not enter. However, conventional physics reveals a critical problem with Einstein-Rosen bridges. They resemble a precarious tunnel through a mountain that collapses under its own weight. The moment anything, even a single photon of light, attempts to cross the bridge, the delicate structure would collapse faster than anything could traverse it. The intense gravitational forces would pinch the tunnel shut, severing any connection between the two regions of space-time. This instability stems from the fundamental nature of gravity itself. Gravity always attracts, creating a compressive force that works against the maintenance of an open tunnel. Without some force pushing outward, the wormhole closes almost instantaneously. In 1988, physicist Kip Thorne and his colleagues proposed a potential solution to this stability problem. They suggested that wormholes might remain open if lined with exotic matter, material with negative energy density. While ordinary matter creates attractive gravitational effects, exotic matter would create a repulsive effect, potentially countering the collapse, like invisible supports holding open our tunnel. Quantum mechanics suggests certain states of matter can exhibit small amounts of negative energy density. The Casimir effect, where quantum fluctuations create a small attractive force between parallel plates in a vacuum, demonstrates that negative energy states can exist in limited circumstances. However, producing sufficient exotic matter to stabilize a macroscopic wormhole remains far beyond current technology. A breakthrough came in 2013 when physicists Juan Meldacena and Leonard Susskind proposed the ER equals EPR conjecture. This hypothesis connects quantum mechanics and general relativity through a remarkable insight. Quantum entanglement between particles, EPR, named after Einstein, Podolsky, and Rosen, might be equivalent to wormhole connections, R for Einstein-Rosen bridges. Here's what this means. When two particles become quantum entangled, they share a connection regardless of distance. When one particle is measured, its entangled partner instantly adopts complementary properties, seemingly communicating faster than light. The ER equals EPR conjecture suggests this isn't faster than light communication, but rather that the entangled particles are connected through a microscopic wormhole. a shortcut through the fabric of space-time itself. The implications are profound. Two quantum-entangled black holes might naturally form a wormhole connection. Even more striking is the possibility that all entangled particles might be connected by microscopic wormholes, suggesting that quantum entanglement could actually be a manifestation of minute spacetime connections. Rotating black holes, known as curved black holes, offer another avenue for potential wormhole stability. Unlike non-rotating black holes, curved black holes possess an inner and outer event horizon. The region between these horizons, the ergosphere, has peculiar properties that might allow for more stable wormhole configurations. In a curved black hole, spacetime doesn't just curve but twist due to rotation. This frame-dragging effect creates complex geometries that, according to some theoretical models, might form stable connections to other regions of spacetime. The mathematics suggest that crossing the event horizon of a rotating black hole might lead not to a singularity, but to a passage elsewhere. Wormholes connected to rotating black holes might potentially allow for time travel. Because certain wormhole configurations mathematically permit connections between different points in time as well as space, they've become a serious consideration in discussions about closed time-like curves, paths through space-time that return to their starting point in time. What if stable, traversable wormholes could exist? Imagine a future where spacecraft could navigate these cosmic shortcuts, reaching distant galaxies without the limitations of light-speed travel. Or perhaps more profound, what if the underlying structure of reality itself is built upon microscopic wormhole connections, with quantum entanglement merely the visible manifestation of this deeper architecture? Despite these fascinating possibilities, immense barriers remain. The intense tidal forces near a black hole would likely tear apart any object long before reaching a potential wormhole. The radiation environment would be lethal. An extreme time dilation effect would mean that even if a traveler returned, they might find thousands or millions of years had passed in their original location. We also lack observational evidence for wormholes. While black holes have moved from theoretical prediction to observed reality, wormholes remain mathematical possibilities rather than confirmed phenomena. Yet the mathematics remains compelling. Einstein's equations, which have successfully predicted numerous confirmed phenomena from gravitational waves to Mercury's orbit, contain these wormhole solutions. They represent a fascinating frontier where our understanding of space-time, gravity, and quantum mechanics converges into profound questions about the ultimate nature of reality. The ultimate unknowable. Those profound questions about reality reach their ultimate expression at the very center of a black hole. What lies there isn't merely strange or exotic. It's a point where mathematics produces impossible answers, and the laws of physics that govern our universe completely break down. According to general relativity, as matter collapses into a black hole, it compresses toward an infinitesimal point of zero volume and infinite density, the singularity. This mathematical abstraction represents a fundamental flaw in our understanding rather than physical reality. When equations produce infinities, physicists recognize they've reached the limits of their theoretical tools. The problem emerges from the collision of two incompatible frameworks. General relativity brilliantly describes gravity as space-time curvature on cosmic scales, while quantum mechanics governs subatomic particles with extraordinary precision. The singularity marks the dramatic battlefield where their conflict becomes unavoidable. As we approach this central point mathematically, the Riemann curvature tensor, measuring space-time distortion, approaches infinity. Tidal forces grow without bound. Energy density skyrockets beyond comprehension. These aren't just large numbers. They represent a catastrophic breakdown in our mathematical description of reality. Physicist Carlo Rovelli captures this crisis. The singularity is not something that exists in the world. It is a place where our current theory breaks down. It is not a prediction of the theory. It is the opposite, the failure of the theory to make a prediction. This failure drives the urgent search for quantum gravity, a unified theory merging quantum mechanics with general relativity. Several theoretical frameworks attempt to resolve this profound puzzle through radically different approaches. String theory proposes replacing point-like particles with tiny vibrating strings as nature's fundamental building blocks. These strings, approximately 10 to the power of negative 33 centimeters in length, the Planck length, vibrate in different patterns to produce the particles we observe. Crucially, strings possess spatial extent, preventing infinite compression and avoiding mathematical infinities. String theory also suggests our universe contains additional spatial dimensions beyond the familiar three. These dimensions remain tightly curled at human scales, but become significant near singularities. Matter spreads through these higher dimensions, distributing energy and preventing infinite densities. Loop quantum gravity offers a completely different perspective, suggesting spacetime itself has a discrete, granular structure at the Planck scale, about 10 to the power of negative 35 meters. This framework describes geometry using quantum networks of gravitational fields called spin networks. Like how water molecules prevent infinitely dividing water, these fundamental atoms of spacetime make continuous division impossible. Physicist Abhay Ushtakar, one of loop quantum gravity's founders, explains space is not continuous, not infinitely divisible. It has a granular structure, but the granularity is so tiny that, for most practical purposes, space appears continuous. When applied to black holes, loop quantum gravity suggests the inward collapse eventually encounters this fundamental granularity, triggering a quantum bounce rather than forming a singularity. Matter compresses to enormous, but finite, density before expanding again, potentially into a new region of spacetime. Causal set theory proposes spacetime consists of discrete events connected through causal relationships, preventing true mathematical singularities while preserving causality. Beyond these specific theories lies a more general principle called the cosmic censorship hypothesis, proposed by mathematician Roger Penrose in 1969. This conjecture suggests that singularities remain hidden behind event horizons. Nature, in effect, veils the breakdown of physics behind cosmic shrouds. However, some mathematical solutions permit naked singularities, points where spacetime breaks down without an event horizon shield. Such exposed singularities would create observational windows into quantum gravity effects, though most physicists remain skeptical about their existence. Recent work suggests the singularity might act like a holographic projection, with all information falling into a black hole encoded on the singularity's surface rather than compressed into a point. This connects to quantum information theory, where information cannot be created or destroyed, only transformed or redistributed. Physicist Leonard Susskind proposes black hole interiors might contain vast amounts of space, more than external measurements indicate. What appears as an infinitesimal singularity from outside might reveal an expansive interior when viewed from within. Carlo Rovelli suggests black holes eventually stop collapsing due to quantum pressure effects, forming ultra-dense, Planck stars rather than singularities. These objects would be incredibly small, but still have physical extent, avoiding the paradoxes of true singularities. Most quantum gravity approaches share one crucial insight. The classical notion of a singularity as an infinitely dense point represents a mathematical artifact rather than physical reality. The true nature of a black hole's core likely involves quantum processes operating where conventional space and time lose meaning. This breakdown of physics at a black hole's center represents both a profound challenge and extraordinary opportunity. Black holes act as cosmic laboratories, exposing the fundamental limits of current physics while pointing toward whatever deeper reality underlies our universe. The quest to understand singularities transcends academic curiosity. It addresses the most fundamental questions. Is space-time continuous or discrete? Can information truly be destroyed? What happens when quantum mechanics meets extreme gravity? The answers will reshape our understanding of reality itself. The black hole information paradox has challenged physicists for nearly 5 decades, becoming the cornerstone problem driving our quest for a unified theory of quantum gravity. As theoretical physicists continue their pursuit of how information might escape these cosmic entities, we're witnessing the emergence of revolutionary concepts about reality's fundamental structure. Recent discoveries suggest that spacetime itself may emerge from something more fundamental. This paradigm shift forces us to reconsider everything we thought we understood about black holes, from their event horizons to their internal architecture. As we peer into these cosmic laboratories, we glimpse not just physics, but the very essence of existence. What